So thank you very much. I want to thank Dr. Gaylor for organizing this excellent session. And I'm very excited to talk to you all today about my research on biogenic worlds. And I'll explain what that is in a moment. And this talk is going to be focusing on Titan and how HCN is produced in its atmosphere. And you can see a list of my collaborators here on the bottom of this slide. Okay, so why, in terms of the origins of life, should we care about hydrogen cyanide? Well, the main reason is that it's a prebiotic source of the building blocks of RNA. So both the nucleobases and the nucleotides can be made from reactions that really just start with hydrogen cyanide. And also, it's a reactant in Strecker synthesis, which produces amino acids, which are the building blocks of proteins. So you have here two key large groups of biomolecules, which can really be produced from feedstocks of hydrogen cyanide. So this really empowers hydrogen cyanide as a key prebiotic molecule. So I want to introduce this concept of biogenic worlds. This is an idea my supervisor, Ralph Pudritz, came up with. These are worlds capable of producing key biomolecules on their own, rather than requiring that these biomolecules be delivered, for example, by meteorites. And we think atmospheres rich in hydrogen cyanide is a distinguishing feature of these worlds for the reasons I mentioned on the previous slide. So in our research, we're really asking the question, was the early Earth biogenic? But, we're atmospheric modelers and we want to model the early Earth. Before we go to a world which has really no atmospheric measurements, because we can't rewind the clock 4.5 billion years, we wanted to model a world which has abundant hydrogen cyanide in its atmosphere today and which has been measured for that hydrogen cyanide accurately using a space probe. So this is where Titan comes in as a hydrogen cyanide laboratory. The Cassini spacecraft went to Titan and took measurements with 4 different instruments at various altitudes and has some really great data on HCN, which is great for a modeler, because you really want to tie your model down to some ground truth to make sure that everything you're doing is accurate and that your chemistry is accurate. So we do disequilibrium atmospheric modeling, and what we need for our tool is reaction rate data. We need to know how fast do all these reactions occur in the atmosphere. And when we started looking at this, we realized that experiments have only studied a portion of the HCN chemistry that occurs in atmospheres. So, rather than go out and do all these other experiments, this is where our strategy came in of using quantum chemistry to uncover all the unknown reactions and add them to the network so that we can simulate all this new chemistry and form a more complete picture of HCN chemistry in Titan's atmosphere and subsequently the early Earth's atmosphere. So what's our method look like? Well, we used density functional theory to explore the entire field of possible reactions for 14 primary species that are found in Titan's atmosphere. Titan's mostly methane, hydrogen, and nitrogen. So you take those species as well as their dissociation products and hydrogen cyanide, which is what we're really focusing on here. Anytime you see a line between 2 species here, that's when I was able to react those 2 species on a potential energy surface. And using this technique, we actually discovered 48 unknown reactions that are just not available in the literature prior to this study. So this really shows you the power of using quantum chemistry, where you can, in the last 1.5 years, I was able to find these reactions and uncover them and calculate the rate coefficient, something that would be very difficult to do in the lab with the same amount of time. What do we do next? Well, we calculated the rate coefficients for these using canonical variational transition state theory. And if you don't know what that is, I put a little animation here on the right. Here's one of my quantum simulations for the reaction of methane with hydrogen atoms. And you can see as you freeze the bond between the 2 hydrogens and let it relax down to its lowest energy geometry, you get this bump in the middle. And that's what the transition state is. It's the highest energy structure for that molecular structure. And this gives you all the information you need to know to calculate how fast that reaction occurs. The larger the barrier, the slower that reaction is going to be able to proceed, and vice versa for the lower barrier. Then from there, we built up our network, which we call our Consistent Reduced Atmospheric Hybrid Chemical Network, KRACHN. This contains about 30% experimental data. So we always use experimental data when it's available, but 70% of our reaction is theoretical calculated data because the data just wasn't there available experimentally. Then we couple our network to a 1D chemical kinetic model, which is developed by the Max Planck Institute for Astronomy, Karan Malaverdikani and Thomas Henning over there. And this handles the radio transfer and runs the chemistry and does the photochemistry. And then we use input parameters for Titan, so things like the top of the atmospheric radiation at Titan and how turbulent mixing occurs in Titan's atmosphere. And that's taken from a Titan model by Eric Herbrard at Exeter University. Okay, so let's get right into the results. Here you see Titan's atmosphere in 1D. In the y-axis, you have the altitude of Titan from 0 to 1,300 kilometers. And on the x-axis, you have the HCN mixing ratio, or the relative HCN in Titan's atmosphere. The Cassini data, the measurements by the Cassini instruments are in yellow, blue, green, and purple. And our 4 models you can see right here with our fiducial model being the black line. So as you can see, our simulation with our Kraken network goes right through the lower part of Titan's Cassini atmospheric data. Then it goes through the first few blue and green points, then veers off to the left of the green and blue points and goes right through the only in situ measurement of HCN in Titan's atmosphere. That's when Cassini dipped down into the upper atmosphere, took a sample of the gas, and put it through mass spec. So we were exhilarated when we saw this because it goes right smack dab through that mass spec point, which is likely the most accurate measurement. And this is just a result of our chemistry. So this tells us, we're doing a good job. Our chemistry is robust because we're able to fit this Cassini data pretty well. I'll just show you one more model here, the red dotted line. What we wanted to do next was we wanted to remove one reaction at a time from our network to reduce this to the minimal network. What is the minimal chemistry that is responsible for HCN synthesis and destruction in Titan's atmosphere? So that really boiled down to about 19 reactions, and you can see a simulation with just those 19 reactions fits over our fiducial line pretty well. Here's the sensitivity analysis I was talking about. So those 19 reactions and the effect on the HCN profile when you remove each one. So the central line here is the HCN profile, and what you're looking at is the change in the profile when removing that reaction. And the largest deviations from the central line are the largest impact on the HCN chemistry. So I just want to highlight one reaction here, the one that's kind of going off the page. This is a yellow line. There's a little inset here. This is cyanide plus methane goes to hydrogen cyanide plus CH3. Clearly this reaction is important for producing HCN in Titan's atmosphere as it's going right off the page. Okay, now I promised you with the title of my talk that I tell you how HCN is produced in Titan's atmosphere, and our strategy has allowed us to do this. So let's get started. In box number 1, we have ultraviolet radiation in the upper atmosphere and galactic cosmic radiation, galactic cosmic rays in the lower atmosphere, dissociating the main constituents of Titan's atmosphere, the methane, the nitrogen, the hydrogen, producing reactive radicals. These reactive radicals then get processed by reacting with each other, and then you have hydrogen cyanide production along 3 main channels, A, B, and C. You see 3 here. So you see here the nitrogens have a superscript, either a 2 or a 4. That's not the isotope, that is the spin state. That tells you whether it's an excited nitrogen atom or a ground state nitrogen atom. And you can see the dominant HCN production is from excited nitrogen atoms reacting with methane at 59% of the initial HCN production. Now I say initial, because if you go down here to number 4, HCN is photodestroyed by ultraviolet radiation. That's a harsh word because all it's doing is popping off the hydrogen off of hydrogen cyanide, leaving you with cyanide. But as you saw on the previous screen with this yellow line going off the side, that's this reaction here. Cyanide quickly recombines with methane to produce hydrogen cyanide plus CH3, and that ends up being the dominant source of HCN in Titan's atmosphere at 36 to 46% of the total HCN. Now I'll just finish by saying that channel C here, which produces 2% of the overall HCN and 4% of the initial HCN in Titan's atmosphere, was actually discovered using our quantum exploration strategy. So that was really exciting to us. This really validated the strategy of going through and really uncovering these unknown reactions before going ahead and actually modeling worlds for hydrogen cyanide production. So thank you for listening, and I'll take any questions you have.
All right, thanks, Ben. Thanks for staying on time here. We've got a few minutes. Anybody have any particular questions for Ben? Looking here in the chat. Yeah, right. Okay, I don't see anything there. Okay, I am curious, Ben, probably more of a practical question in terms of what sort of challenges does one face, not being a modeler myself, what sort of challenges does one face getting a hold of this kind of data? Your program is obviously dialed into that collaborative network, and sometimes those data sets can be challenging to get a hold of. So I'm just kind of curious, was there pain associated with this? Or?
Yeah, and actually something that you mentioned in your talk really rang true to me when you're saying methods development, you know, being the, that's really the most time consuming portion of this. It took me about 1.5 years just to develop the method to calculate these ray coefficients at a level of accuracy that was consistent. And, you know, when you're using quantum chemistry, there's a lot of different methods, and like quantum methods and different basis sets. These are just like, you know, the amount of orbitals you use when you're simulating. And, you know, you can use density functional theory, but you can also use ab initio methods. There's all these different kinds of methods, and they all have pros and cons for different types of reactions. But we wanted to be consistent, and I didn't realize how difficult that would be, trying to be consistent. Eventually, we landed on one that was most frequently within about a factor of 2 of experimental data when it was available. So, you know, this is kind of in line with your typical uncertainties with experiments anyway.
Sure.
So that really was the longest, you know, most painstaking part of this research. But now that we have it, you know, we're ready to go. We can just keep simulating now. So it was worth it. But yeah.
Now you can crank it out. But I've just started working with a couple of computational chemists, and I certainly know enough to get into trouble, but I'm really starting to appreciate, oh my God, what a special pursuit this is, and how sort of painful it can be. So I am seeing something here from Bruce Damer here in the chat box. I'm assuming you can see it. Yep. I'm assuming you can see that, or I can read it, whatever you prefer.
Let's see. Sorry, I don't have the chat box open. You mind reading it, actually?
I'll do it. So Bruce asks, how can a biogenic atmosphere fill some of the gaps for nucleobase delivery by meteorites and the sourcing of nucleotides? Is his question.
Yeah. So Bruce has a little bit of an insight into our kind of the history of our work. We used to do a lot of work on meteoritic delivery of biomolecules, things like nucleobases and amino acids. But you know, when we're doing that research, it seemed to be a plausible source of about, you know, parts per million level concentrations of these things in ponds, but it was just one single feedstock. And in thinking about getting life started with one feedstock, you know, it seemed like it might be difficult. You know, it maybe had to be that way, but it might be difficult. What would be better would be to have a consistent source. So this really motivated our approach to look to the atmosphere as a source of prebiotic precursors like hydrogen cyanide, which can then rain down into ponds and provide a consistent source of these precursors. So you can get aqueous chemistry producing the same sort of biomolecules like nucleobases and nucleotides. So right now we are actually modeling the early Earth. We are doing this HCN chemistry and formaldehyde chemistry actually in the early Earth atmosphere, raining this stuff down into ponds, and we're redoing our nucleobase synthesis using thermodynamic methods, and we're going to compare with our meteoritic stuff. So I'll be very excited to share that research in the coming months when it's done, and I think it's going to be exciting to y'all. So yeah,
very cool.
Tuned.
Very cool. Good question, Bruce. Thank you for that. Yeah, this is all very cool to me as I try to learn more about the computational stuff, you know, so very exciting. All right. Thanks so much, Ben, for a very intriguing talk. I have a